group actions. We've seen what a group action is before. We've looked at a number of examples of group actions. Now what we're going to do is we're going to go a little bit deeper. We're going to talk about group actions, permutations. We're actually going to apply this to a lot of very important theorems about the structure of groups. So I'm going to dive right into this with this big theorem here. So here's the setup. I have some group, G. Group. A non-empty set. And I'm going to denote by SA the bijections from A to A. Okay, so that's my notation in this theorem. Remember, if this is a set of n, if A is a finite set that has n elements, then this is the same thing as Sn. Well, these are just permutations. SA is just permute. So I've got my group G, I've got some non-empty set A, and S of A is permutations, if you will, of A. Then there is a bijection between actions of G on A and homomorphisms from G to SA. Then there is a bijection, or if you like, a one-to-one correspondence between actions of G on A and homomorphisms from G into SA. And the way that this is given is if dot is an action, then it is G dot A is phi of G of A. Where here, A is in A, B is in G, and phi goes from G into SA. So the action of G on A is whatever phi of G is acting on A. Now remember what phi of G is, actually is, this is a function that is a permutation of A, so this takes A to some other element here. And actually, I think in this case, this is one of those situations where I think going through the proof hopefully will help us understand what this is all talking about. Proof. Suppose first phi from G to SA is our homomorphism. Right? Because remember what we have is we have a one-to-one correspondence between actions of G acting on A and homomorphisms from G into the permutations of A. Right? So suppose first that we are given from on high this homomorphism that goes from G into SA. Then if we define an action on A, just like we said here, let's think about what this does. G acting on A says, okay, shove G into this phi here. When I shove G into this phi, I get a permutation of A. So this takes this A to some other element of A because it permutes the set A. The function from G cross A into A, right? Input a G, input an A, and you output an element of A, right? And I want to show it's an action, right? I want to show that this circle definition here is an action. G1 circle, G2 circle A is actually, you know what? I'm going to start it this way. I'll start it with the other hand. Let's do G1, G2 circle A. By definition, what this is this is phi of G1, G2 acting on A. Right? Well, what do I know about phi? It's a homomorphism, right? So I can pull this bit apart because phi is a homomorphism. This is phi of G1, phi of G2 of A, which is phi of G1, phi of G2 A. And this is phi of G1. By definition, this is G2 circle A. That's the way it's defined. And by definition, this is G1 circle G2. Okay, so it's got that part of the action going on. So G1, G2 circle A is G1 circle G2A. And what else? Does anybody remember what else I got to check to make sure this is bona fide action? Yeah, it's got to behave well with the identity, right? So let's see what happens there. E acting on A is phi of E of A. But this is a homomorphism, right? So it takes the identity to the identity. So this has to be the identity function. SA, right? And the identity function takes everything to itself. So that's A. So this is a bona fide action. Right. Now, so what I've shown is, if I start with a homomorphism, this definition gives me an action, right? Now I want to start with an action and show that this assignment gives me a homomorphism. Suppose that we were given the action. So let's now suppose so I've got to think about this sort of thing. Now suppose we start instead of with the function, or instead of starting with the homomorphism, suppose we start with the action. And this is an action, so it satisfies the properties of an action. I want to show that this gives rise to a homomorphism in permutations. So I'm going to define the homomorphism that I want by my input is an element of the group. This, I haven't told you what this is yet. I'm just going to call it pi g for now. It barfs out this pi sub g, right? And I want this to be a permutation. And this is given by pi sub g. It's a permutation of the set A. Pi sub g of A is G circle A. So this permutation here that I need to, or this permutation here just does, I think what you would think comes naturally. Pi sub G of A is G acting on A. Now, Let me point out that this is in fact, let me point out that this pi g actually is a permutation of A. So, notice that pi g of A equals pi g of A prime implies G A. Everybody agree with that? So if pi g of A equals pi g of A prime, that means that G circle A is G circle A prime. Now hit this on the left by G inverse. And this implies that they prime. So pi g is 1 to 1. Everybody okay with that so far? Any questions? Okay, next step. What I'm trying to show here is that pi g is a permutation. I've already shown that it's a 1-to-1 function from A to A. How about on to? Anybody figure out? Tell me what I could pick for x such that pi g x is equal to A. Well, sort of. Let's let x G inverse circle A. Right? Notice that the group, this is a group action. So G inverse X makes sense. It's some element in A. If you look at pi G of X, this is pi G of G inverse A equals G circle G inverse of A, which is A. So in particular, what we've shown is pi G is a permutation. It is both 1-to-1 and onto it's a bijection, right? Right. Let me also point out I need to show so what I've shown is that the output makes sense. The output is indeed a permutation. I need to show that this is a homomorphism, right? I mean, I did claim that phi is a homomorphism. So to see that, so well, let me point out first that pi GH, if you look at pi GH of A, this is GH acting on A, which is G acting on H acting on A. Which is pi G of pi H of A. So in other words, composing pi G and pi H does the same thing as just pi GH. So in other words, everybody okay with that? Yes.
Why do we need to show that phi is a homomorphism when we've been treating it like one?
Oh, no, we defined this function here. In the first part that we did before, we started with a homomorphism and showed we got an action. Now we're starting with an action and we define this function. And what we've shown is the output is indeed a permutation, so at least it's going where I say it is over here in SA. But now I'm going to show this is actually a homomorphism. This assignment as it is doesn't guarantee, but now with this fit right here, we've got it for the following reason. If you look at phi of GH, this is pi GH, which we've just shown is pi G, pi H, which is phi G, PH. So phi is a homomorphism. G into permutations of A. Any questions on that? Why is this a bijective correspondence? Well, if you start so this is in the notes as well, and I'll ask you to check this because I think it's a good exercise. But if you start with an action and then derive our phi from it, and then get the action for phi, we recover initial action. Actually, maybe we should go through this. Let me clarify what I think. So suppose we have phi G cross 8A. Okay, so how do we get this phi? Well, this gives us our phi from G to H, and if you remember, not G to H, I'm sorry, G to SA, phi of G was pi G, right? That's the way we started with the action, and then we got this permutation where pi G of A is G circle A. Now, take that phi from G into SA and recover an action from it. And the action, the way we did that was the G acts on A as phi of G of A. And notice this gives us back our original action here, right? So when we start with the original phi, or start with the original circle action, we get this phi, and we do the phi, this homomorphism gives us action this way, which is the original action. If you start with phi and get an action circle and then go back to phi, you get the same thing. And that shows actually that the correspondence is in fact bijective. So it's a one-to-one and onto. And that proves the theorem. So this is the thing to think of. Any action on a group can be thought of in a certain sense as a homomorphism into the permutation group of the set that you're acting on. And this is going to be quite useful to us later. Okay, any questions? Okay, so here's some definitions. definition. I may have mentioned some of these too, but it's not gonna hurt anything. Let G act on A. So, define the kernel of the action. The set of G and G, such that G acting on A is A for every A in A. What the kernel of the group action is, it is everything in the group that leaves everything in the set alone. Everything. Can anybody think of something that for sure is in the kernel of any action? Absolutely. The identity is always the kernel of the action. The identity leaves everything alone. Is there more? Sometimes yes, sometimes no. Two, for all A and A, the stabilizer of A is so the stabilizer of a particular element is everything in G that leaves that particular element alone. Notice for any element A, the stabilizer is all, the identity is always in the stabilizer. Everybody agree with that? So here is kind of an important, this Rubik's Cube is not solved, right? Has anybody ever played with one of these things? It may make you cuss a little bit, right? The first thing, how many of you can get like just one row, just like this right here, maybe correctly, right? Then it becomes hard because after you've solved one side, you got a problem because you want to make an omelet and it's, boy, it's hard to break those eggs, isn't it? Right? Because once you've got this nice white pristine side, in this case, all solved, maybe you want to get the rest of it. So maybe it's something like this and you want to get another layer, right? Because it's not solved here. This is why stabilizers are important, right? You want to find elements of the group here, the rearrangements, that leave what you've got solved alone. You want to stabilize the top, right? You want to act on this thing without screwing this up, right? So for example, something in the stabilizer here, this move right here doesn't interfere with the top, right? And I'll do that move again, essentially. I've done things that stabilize the top, but they permute everything else. Now I've got two layers, right? So oftentimes things that are left alone by various actions turn out to be important. And that's why this is going to be an important, it's going to be an important part of our repertoire here. 3. We say G acts faithfully on A if the kernel of the action is trivial. And by trivial, I mean, yeah, and the only. And yeah. And I don't know where that terminology kind of, whatever group theorists came up with that was obviously having problems with their significant other. But anyway, what it means to act faithfully is the kernel of the action. The only thing that leaves everything in the set alone is the identity. Okay, any questions? If you hear this terminology, here's another thing that we need to address. If G is a group, no, definitely. Do it. Go there. Oh. Let G be a group. A permutation representation of G is, there's not too much to this, is a homomorphism. G into SA for some set A. So a permutation representation of a group is just a homomorphism from G into A. So what you do is you take some group G and you write it as a collection of permutations. Let me give you an example of a permutation representation that you've already seen. Examples of permutation representation. Example. Let G equal D5. Here is a permutation representation of this. Okay. You remember playing around with this pentagon, right? The dihedral group. And notice we proved that we proved that, so actually, let me write this way. I'm gonna go here. So the permutation representation that I'm talking about here goes from D5 into S5. Right. Your input, your abstract group, if you will, is this dihedral group written this way, and it goes into S5, which is a permutation group on, in this case, your set A is just the set 1, 2, 3, 4, 5. And here's the way the homomorphism works. It takes R to 1, 2, 3, 4, 5. It takes S into 2, 5, 3, 4, which is flipping about the y-axis. And you can actually check that this is a homomorphism. In fact, it's a 1-to-1 homomorphism from D5 into S5, and it's a permutation representation. And perhaps this example shows why it's called a permutation representation, because here we can just think of all the rearrangements of the pentagon just as these permutations. This is the rotation, this is the flip, and then there's 8 other ways that you can combine them. Okay, any questions on it? Okay.
I have a question.
Yes.
How can we guarantee that's 1-to-1? Because shouldn't some
This
function like,
particular, you can't. right? I didn't say it had to be 1-to-1, but in this particular case, it is.
Did you say that in this?
Was
Did
that?
you say it was onto?
Oh, no, it's not onto, but it's 1-to-1. Yeah, S5 is much bigger, right? S5's got 120 elements in it. And this little thing right here generates a little subgroup of order 10 inside of there. Right? And so the 1-to-1 map just takes, it'll take R to this, S to this, and then you can, any product, R squared S would be, goes to the square of this times this. And so. Okay. Other questions? Okay, here's another definition, orbits and transitive actions. Definition. 5.5. Let's suppose that G acts on the non-empty set A. Number A. If A is an element of the set, then the orbit of A is, and I'll write it this way often, orb A. This is just the set of every place that A can be pushed by G. So you take every element of G and act on A and see where it goes, collect all those elements, and that's the orbit of A. It's everywhere that A can go being pushed around in the set by the action of G. What is one thing that for sure is in the orbit of A? A itself, right? Because, for example, the identity pushes it to itself. Yes.
Okay, that was my question.
Number two. We say G acts transitively on A if there is only one orbit. We say that the action is transitive if there's only one orbit. Here's an equivalent way to think about it. For all A and A prime in A, for any pair of elements A and A prime, there exists G such that G pushes A to A prime. So that's another way to think about transitive action. Given any two pairs of elements in your set, take any one of those, that pair of elements, there's something in G that pushes the first element to the second. That's what it means for an action. Transitive. Okay, any questions? Yes.
The image of the orbit, like, are those like similar?
Sort of, right? Because, so remember, this is an action. So your input is something in G, something in A, and you get something in A, right? The problem is A itself is not a group, right? But we can sort of count this, right? So what this means is the image under that function right. So if you take a single element of A and you vary the elements of G, if that is sort of onto the A, that's another way to think of it. Right. So let me give you an example here. And I'll give you a non-example, something that's not present. Um, uh, let, let Z6 act on itself by conjugation. Well, actually, A being a billion group. I'm getting slow, confused to say, a billion group. So suppose I have a billion group, and I'm gonna let it act on itself by conjugation. Right? So we've seen before earlier, the conjugation is actually always a group action, right? But if the group is a billion, what can you say about old gag here? It is A, right? This is G inverse A, which is A. So if we have this action and the group is a billion, then the orbit of anything is just itself. Right? So the only way that this can be transitive is if the group is only the identity, right? Because if the group's got more than one element, then there's no way that you can have it be just one big orbit, right? Everybody okay with it? Okay. Theorem 516. Let G be a group acting on subset A, not empty again. I am going to declare A is related to B if and only if you declare A is related to B if and only if GA equals B for some G and G. This relation is an equivalence relation. Then tilde is equivalence relation. And I get this other, but really cool result that the number of elements in the equivalence class. So if you have an A in set, the number of elements in the equivalence class of A is the same thing as the cardinality of the orbit of A, which, yes.
So with that, I was gonna ask earlier, but you didn't see me, it's okay. So does the orbit form a partition? Is that what this is?
Oh, yeah. So that's very astute. Here, let me write this down and I'll address that. He's right, because what happens is once we do this, then that means that the separate orbits will actually partition the set A. Yes.
The orbit of some element A is some collection of elements in A.
That is correct.
So
Actually, you know what? Let me go ahead. Go ahead.
we can find your equivalent statement right there for any A prime in A. There exists a G such that G of A goes to A prime. Wouldn't that mean that the orbit is all of A?
That's right, and that's what it means to be transitive, right?
So when you say there's only one orbit, you're not saying the orbit has only one element. You're saying
There's a single orbit that consists of the orbit of some element of that. That's right. And I like to think of this result here is, so we're gonna show that this tilde is an equivalence relation, so it partitions A into, it partitions it into basically the distinct orbits. And the size, if I walk up to you on the street and give you an A, the size of the equivalence class of A, that's synonymous with the size of the orbit of A, is the index of the stabilizer. So you take the group G, you divide out by the orbit, or the index of the stabilizer. This is even true if this is an infinite set as well, and we'll see that. I like to think of this as the length of orbit is the index of the stabilizer. I'm going to give you this without, well, I'm going to prove the theorem, but I'm going to give you an example that I want you to verify for yourself. And we're going to see a theorem that actually does this for us later, but I think you should probably do this hand computation yourself. In S3, act on itself. By conjugation, I think. That is, some G acts on X, G acts like that. I'm going to write down for you without proof what the orbits are, but you should be able to just compute these yourself. And actually, there's a takeaway. I'll give you a little bonus just for showing up today. I'll give you a bonus. Here are the orbits under this. One of them is the identity, right? Because what happens when you conjugate the identity with anything? You get the identity. That is a singleton orbit by itself. That's one. Another orbit is 1, 2, 1, 3, 2. These are all conjugate for each other. And there's one other orbit. This has 3 orbits, and as you predicted, notice it's a partition, right? There's no overlap, and everything in S3 is in one of these. In fact, here is my bonus that I will just give you now as kind of a statement, is any 2 elements of Sn, right? This is just S3, so it's an easy example. Any 2 elements of Sn are in the same orbit. They're conjugate, under conjugation, they're in the same orbit, if and only if they have the same cycle type, right? And by cycle type, I mean they have the same number of cycles of the same length, right? So for example, 1, 2, 3, that's just cycle type 3. You have 1, 2, 3, 4, 5, 6. That's cycle type 3, 3. These 2 will never be conjugate because they're actually different cycle types. So that's something that that I haven't proved for you, but you can just put that in your tool basket. Okay, let's begin by showing that this is an equivalence relation. Any questions for us? Yes.
Okay, when we use the index notation, I can't remember. Does that imply that the stabilizer is normal in G or no? I'm wrong.
No, it
Okay,
doesn't.
no.
No, it's just, so that's actually a great question. It does not imply that it's normal. Because all you really need, we're just counting left cosets. I did not say that G mod GA is a group. I'm just counting left cosets. Okay, so. Okay, first, I guess I need the equivalence relation. proof, I claim tilde is an equivalence relation. Number one, notice that the identity acting on A is A. Therefore, A is related to A, and you get reflexive. Number two, suppose A is related to B. Let me check which way I did this one. Okay, so that means that G acting on A, B, for some G and G. Great. Now, I want to get the turnabout. I want to get that B is equivalent to A. So how do I do that?
The inverse for G.
That's right. Just hit this bad boy with G inverse on both sides. And so I get G inverse acting on G, acting on A, is G inverse acting on B. And this, of course, is G inverse G acting on A, which equals A. Therefore, A is obtained by something acting on B. So B, A, and this is symmetric. And lastly, I guess we need transitive. So let's suppose A is related to B and B is related to C. So there exists G and H and G such that G acting on A is B and H acting on B, C. Right. So let's see what I should do here. It looks to me like if I put an H here, yeah, that's what I want to do. H acting on G acting on A is H acting on B, which is C. And this is HG acting on A. Therefore, A, C. So that part of the proof is done. We know that it's an equivalence relation. Okay. Any questions on that so far? Questions? Yes.
Can you just like go slower through the transitive one again?
Well, so this right here means that by definition. Agreed? And this right here means this. Right? So what I did is I'm going to put an H circle on this. Get H circle B. This step here, right? But H circle B, let's see. Now collapse this back. This is HG. Okay? And so by definition, this means that A, because there's something in G acting on A that gives you C, so A is equivalent, or is related to C. Other questions? Okay, we'll get a start on this. If we have, so let me kind of set things up here. And we'll finish this up next time. Notice if A is in A, then the equivalence class of A, so let me make it clear that I'm doing this. Let's think about what this is. This is the set of all crap in A such that X is related to A. Oh, well, actually, I'm gonna do it the other way for convenience. Doesn't matter because it's symmetric. Everybody okay with that? And what does this mean? This is the set of X in A such that right? So basically, this is just the set G, A, G, and G, which is the orbit. Right? So what we've established here is that the equivalence class is exactly what I told you what it is. It's the orbit. We'll take apart the business about the index of the stabilizers, the length of the orbit next time. Any questions? Any questions? Okay, I'll see you folks on the phone.